All right. We're here with Jason Rhodes from the NASA Jet Propulsion Laboratory. What's your main title again?
My title at NASA is at NASA JPL is Senior Research Scientist, but I want to stress that I'm speaking on not on behalf of NASA today. I'm speaking on behalf of myself and my own job and my own interests. But I am a research scientist at NASA.
Well, appreciate you so much for being here. A buddy of mine, he loves space and science and technology and all that stuff. And he actually told me it's not Jet Propulsion Laboratory, it's JPL. He said they prefer JPL to Jet Propulsion Laboratory. So,
yeah, I think most of us call it JPL. That might be due to the fact that for those that know the history of JPL, the history is in the 1950s, some Caltech people were doing experiments in rocketry, not jet propulsion, rocketry, and they moved to a space somewhat far from Caltech, about 5 miles or 10 kilometers from Caltech for safety, because they were testing these rockets, and that's the site that eventually became JPL, which, as I said, was originally a place for testing rockets and things that go in space. And so JPL has always been, I feel, a bit of a misnomer, because it's more of a space lab than jet propulsion laboratory.
Well, speaking of space, we're here today to talk about one area which you are heavily involved in, the Euclid Space Mission, which I understand is scheduled for launch 2022, like mid.
That's right. Yes. So Euclid is scheduled to be launched from Kourou in South America on a Russian rocket provided by the European Space Agency, who's leading the mission in sometime in mid to late 2022.
So I first learned about the Euclid Space Mission, or heard about it, I think it must have been 5, maybe 4 years ago. And as a Mason, anytime you hear the name Euclid, or you hear about something related to geometry, is going to pique your interest. I sent you some pictures. We have Euclid's 47th problem displayed prominently in our Masonic lodges. It's in a lot of our symbolism, and geometric ideas are pretty prominent in Masonic lodges, going back to our, roots as actual Masons, as stone builders. Obviously, going back as far as you want, if you're a Mason building the pyramids, you better know how to make a right angle. You better have an understanding of geometry. Especially back then, the pharaoh might not be happy with a lopsided pyramid. So I've always been fascinated, and since I joined Masonry, more so with geometry and how it helps us understand the world. But in your case, naming the project Euclid, it indicates that geometry helps us understand not just the world, but the whole universe. So can you talk about first what the Euclid Space Mission is, what its purpose is, and how the name Euclid was developed?
Yeah, so Euclid as a mission goes back 15 or more years as a mission concept. And the idea was to study the contents of the universe. And specifically, the primary content of the universe is this substance or property of the universe that we call dark energy. And this dark energy is making the universe expand faster and faster as time goes on. So we've known for 100 years that the universe is expanding, it's getting bigger. But we've only known for about 20 years that expansion is getting faster and faster. Now, that fact that that expansion is getting faster and faster is sort of counterintuitive. And the reason is, you think in a universe where there's gravity, and we know that there's gravity in the universe, that's going to want to pull everything together. That's what gravity does. But instead, we see, if we look at the very wide universe, we see that instead of the universe being pulled together, it's being pushed apart by something. We don't know what that something is, and we give the name of our ignorance of what that is. We call it dark energy. And so we want to study that. And so in Europe, at the level of the European Space Agency, which is sort of the European equivalent to NASA, there was a call for mission ideas about 15 years ago. And two separate groups put in mission ideas, one to study dark energy in one way and one to study dark energy in another way. And both ideas were selected for more study. And after a few years of study, they merged these two ideas, which had two different names. And so the merged team, which was selected to go ahead and build a space mission, was asked to come up with a name. And so at that time, they were looking for a name. A lot of times, space missions have names that are acronyms, but more often what we've been doing in the last few decades is we've been naming them after famous or influential people. And so they were looking for a name of someone famous and influential in this area that was, since it's a European mission, also a European name. And one of the properties of this dark energy is it affects what we call the geometry of the universe, how the universe looks, how the universe expands over time. So they thought, what more apt and appropriate name for studying the geometry of the whole universe than to call this mission Euclid, who, as a Mason, I'm sure you know, Euclid is considered the father of geometry. And when we talk about space as we think of it, with right angles and that sort of thing, we talk about Euclidean space, the Euclidean three-dimensional space. So Euclid is really a name that is synonymous with geometry, and given that we're trying to study the geometry of the whole universe, Euclid was the name that we picked, and we're really excited about this name and the connotations with geometry that you mentioned.
And we just passed the 100-year anniversary, I believe it was 2017, of the general theory of relativity, which I always, one thing I always hear about that is it changed gravity to geometry, is a quote I've heard, I think, a few times about that. Or Albert Einstein changed, gravity into geometry. Could you talk a little bit about that? And is that at all related to the Euclid mission and what it's attempting to study?
Absolutely. So as you mentioned, we learned about 100 years ago with Einstein's general theory of relativity, which is still the theory of gravity that we use today. And I should say before that, it had been hundreds of years of using Newtonian gravity from Isaac Newton, his theory of gravity. And general relativity, Einstein's theory of gravity, is what we'd call maybe a revision of Newtonian gravity that gives more precision, especially over large distances or with very, very massive objects, lots of mass. It tells how gravity behaves. And what general relativity says, in a nutshell, is that gravity is a geometric property of space-time. That is, gravity bends space, so it changes the geometry of space. And some of the most spectacular examples of this bending of space and the geometry of space are through a process we call gravitational lensing. That's where a very massive object, and sometimes it could be like our sun or a whole galaxy of clusters of galaxies, bends the light coming from behind it. And so what it's really doing is it's bending space, and light is traveling through a straight path through space, but it's space itself that's bent. And so the path of the light to us appears curved because space is bent. Geometry of space is changed. And so it's that studying that geometry of space that we're trying to do with Euclid. And when we are doing that, we're doing sort of two things. First, we're looking at the properties of space, and we're assuming that general relativity is correct. That is, we're saying, okay, if general relativity is the correct theory of gravity and really describes how the universe looks and how the geometry of the universe behaves, what should we see, and what does that mean for this dark energy? But we're also going to run the Euclid experiment in a robust enough way to say, all right, what if general relativity isn't completely correct, and we need another revision on top of that? And we call those potential revisions modified gravity. And in the same way as Einstein's theory of gravity replaced Newton's by refining it, we think that there might be some refinements to general relativity. As we wouldn't say general relativity is incorrect, we would say it's incomplete. And there may be further refinements. And so with Euclid, we're going to be able to test both what dark energy is doing if our assumptions about general relativity are correct, but we're also going to be able to probe those assumptions and say, is this the correct theory of gravity? Is this really how space is bent by matter?
Now, keeping in mind, I'm not very smart. The viewers might be, but I'm not. Can you explain how will the Euclid mission do this? What type of technology is used to measure this lensing and to measure kind of the geometry of the universe? I'm assuming you can't just go up there with a really big, square and compass. Though we have some if you need any. We have plenty of square and compasses lying around our lodges.
No, we're going to use 2 different cameras and 2 different techniques to study this. And so I'll tell you first about the 2 cameras, and because those are pretty straightforward. We will have 1 camera with optical CCDs. Now, CCDs are charge-coupled devices. These are just the typical cameras that you would find in your cell phone. We both have one in our computer that's taking our images now. But instead of having a single CCD with, say, 10 megapixels, Euclid's visible camera will have 36 CCDs, all mosaicked, all put together, and each of those will have about 16 megapixels on them. So it's got a huge number of pixels, and so what that's going to do is it's going to allow us to take pictures in just a few years, 6 years, pictures of almost half the sky at a very precise resolution. So that's Euclid's visible camera. It's got a same camera, or same size camera, with near infrared detectors. These are detectors that essentially see heat. And they're actually becoming more popular now as we face this pandemic, because they can take your temperature, for instance. And so I think as we move forward to people going back to work and stuff, I think there will be a lot more infrared cameras at various public places taking people's temperature and making sure it's below, normal body temperature. They don't have a fever. But it will also have an infrared camera, and these 2 cameras are looking at the same spot on the sky through an optical element called a dichroic. And what a dichroic means is it's basically a piece of crystal that, when the light goes in, the visible light splits off one way and it goes to the visible camera, and the infrared light splits off another way and goes to the infrared camera. So both of those cameras are looking at the same spot on the sky. And the reason we're doing this is we want to look at a wide range of light wavelengths to get more information about the galaxies. So those are the 2 cameras we're going to use. And the 2 techniques we're going to use on Euclid are called galaxy clustering and gravitational lensing. And so I'll tell you about galaxy clustering first. With galaxy clustering, what we're going to do is we're going to look at the positions and the motions of tens of millions of galaxies over about half of the sky. And it's the precise locations and how those galaxies are clustered that tell us about the history of the universe. Galaxies become more clustered as the universe goes on due to gravity, but they tend to be pushed apart, excuse me, due to the dark energy. So by looking at the positions and how the galaxies are clustered, we're going to be able to study both the effects of gravity, that is general relativity, and the effects of dark energy, and look at how they interact with one another. So that's one of the two techniques. The other technique we're going to use is called gravitational lensing, and that's this bending of light by massive structures that we see in the universe. And by looking at how the shapes of galaxies are slightly distorted by this bending of light, we can figure out, excuse me, we can figure out how much stuff, how much matter is between us and these galaxies, and where that matter is positioned in the universe. And the position of that matter, again, is given by the clumping caused by gravity versus the pushing apart caused by dark energy. So by looking at where the matter is in the universe, we're going to have another way of measuring the effects of both gravity and dark energy. So it's this gravitational lensing and this galaxy clustering, these two different techniques that are going to allow us to study the universe with Euclid.
Speaking of, I mentioned earlier, you can't just go up there with some compasses and do a measurement. But I did get a kick out of when I went to the NASA website on Euclid, which you sent to me. One of the pictures I saw was, I'm assuming it's Euclid in the universe with a pair of compasses measuring the geometry of the universe, which I got a kick out of because compasses are also a very common Masonic symbol. You hear all the time the square and compasses. Do you have any information, or what do you know about that image? Do you know how it was? Who came up with it? Or?
We did not. Cool. I'd have to look at the history of that image. That's pulled, if I remember correctly, and I don't want to be quoted on this, I think that's pulled from an image that's perhaps a medieval painting or maybe a later painting called the School of Athens or something like that, where there's a number of different famous philosophers put in a famous painting. So that image that you're talking about of Euclid measuring the universe is from a very famous painting, being the Euclid mission. Pulled that image from there and then superimposed it on space. So instead of measuring the ground and the world around him, we have a picture, of course, of Euclid measuring the properties of space itself, which is emblematic of what this Euclid mission is meant to do.
I think it's such a fascinating juxtaposition between, the ancient and the modern, right? You have Euclid, the ancient, an ancient geometrician, and kind of the modern universe and satellites, and putting his name to something he probably could not have ever imagined, or would not have any, concept of the idea of sending satellites out into space. I guess that goes to, this constant building on science and understanding from Euclid through to now, how we're always building on what came before and expanding on it. And I guess my question is, what do you hope that this Euclid mission does for future, when people are looking back on it? What do you hope it's able to contribute to science and to understand the universe and to future generations? I know you talked about, it could help us better understand general theory of relativity or make it more complete. You mentioned right now it's not incorrect, but maybe incomplete. So when future generations look back on this mission, what do you hope they say about it, and how do you hope they perceive it?
Yeah, I can think of a few things along those lines. And one of the really exciting things for me about a mission like Euclid is when we think of future generations. If I think of a generation of astronomers just 10 years from now, for instance, they're going to use the Euclid data, these Euclid images and the spectra of the galaxies that we'll collect with this visible and this infrared camera. They're going to use these images for many, many things beyond the dark energy. And in fact, if I think of 10 years from now or 15 years from now, going to look at the number of papers, scientific papers written with the Euclid data as the primary data set, that is, people say, take the Euclid data and go look at it. I think there will be dozens or, of order 100 papers on cosmology and dark energy and the contents of the universe. But I think there will probably be 10 times more papers on other aspects of astrophysics. And what I mean by that is when we look at the shapes and the positions of these galaxies, the primary reason we're doing that in Euclid is to study the contents of the universe and look for dark energy. But in doing so, we'll gain a ton of information about how galaxies form and how galaxies evolve and how stars form and how stars evolve. And so we'll learn a lot about galaxies and stars. And I think there will be many hundreds or even thousands of papers from Euclid data on these other areas of science, which aren't the ones that are our primary concern. So if I think about the impact of Euclid in the next decade or 2 decades, it's much greater than just on dark energy. Now, another aspect of that is one that I touched on and then you touched on, is that we're always building on previous theories in science. And one of the misconceptions I often see of scientists and science is that scientists don't want, they have a theory and they don't want to have that theory proved wrong or incomplete. They're always trying to show that this is correct. And that's really not how scientists operate. And I can say that almost all the scientists I know would love to be the ones to say, I found out where general relativity was wrong or where general relativity was incomplete, and I'm the one that found this new theory that works a little better. So scientists always want to find the new thing that works a little better, and they want to build on rather than just prove correct their predecessors. We want to build on it. We want to find something new. And I think with a mission like Euclid, we really have the potential to do that, because we really don't understand very well what dark energy is or how it behaves, especially how it behaves over time in the universe, over the last half of the age of the universe. We don't understand that. And so I think a really lasting legacy of Euclid will be a much better understanding of how dark energy behaves, and a much better understanding of whether Einstein's theory of general relativity is a complete theory of gravity to the level at which we can measure with something like Euclid, or whether it's slightly incomplete and we have to make some modifications. So I think that's where Euclid is really going to make a difference in cosmology.
I really like what you mentioned in your answer. One of the things you mentioned was, scientists they're not just looking to confirm what they, they're not just looking to confirm what they suspect or what their theory is. They're looking to either confirm or not confirm. They're looking just for what the answer is, and whether it conforms to the theory or it doesn't, they're always willing to revisit their hypothesis and revisit their theories and modify if the evidence supports the modification. So it's that, lifelong learning and being willing to adapt or modify something if the evidence doesn't support or supports in a different way. How important do you think that scientific model is just to critical thinking skills in general? We live in a world of social media and bubbles, and a lot of people will seek out, they type in www.imright.com to seek out, to confirm whatever they already believe. Whereas NASA and science is more interested in, they have a hypothesis, but they'll revisit it or modify it if the evidence doesn't support it or supports something else. So how important is that, do you think, just to the world in general and how we move into the future?
That's a great question. And I think it speaks to your you're taking sort of these scientific principles and you're saying, how could we apply them more broadly in our daily lives? And I think the way scientists think, they question authority. And by saying question authority, I don't mean they're questioning the authority of the government or the authority of people, their hierarchy at work, or for younger people, questioning authority of their parents. I'm not talking about that. I'm talking about a question in a good way, the things that they've been told before them. That is the authority of scientific progress from hundreds of years ago to now, and we want to question that and say, is this complete? Are there other experiments we could do to show this is wrong or incomplete? And I'll tell you, for general relativity, for instance, you mentioned before, it's about 100 years since we had this theory of general relativity from Einstein. For that 100 years, there have been many, many scientists and experiments saying, I want to see if general relativity, if I can prove that general relativity is wrong. And there's just as many people saying, I want to see if I can prove it right. But the way scientists think is they think, it's going to be a really big splash if I can prove it wrong. So it's not that we think it's wrong, but we want to question, what are the ways we could poke at this theory? What are the ways we could test it? And I think that's probably an important part of critical thinking for people to take into their everyday lives. If you're told something, I think it's always good to be a bit skeptical and say, all right, what are the ways that this could be correct? And what are the ways in which this might not be correct? And I think a lot of people do this, in their everyday life without even really thinking about it. And so we're actually ingrained with this sort of scientific process. If you look at the weather report and it says, oh, it's supposed to be raining right now, and you go outside and the sky is completely clear of clouds, beautiful blue sky, you say, okay, I think that weather report was wrong. And that sort of thing where you make an observation and you say, okay, the information I was given before was perhaps not correct. And that doesn't mean the person lied to you or the person did a bad job. It just means that sometimes we have incorrect or incomplete information. And as scientists, we're always sort of questioning the world around us. And I think people would do well to question the world around us, question the things that they're told, and try to understand the reasons for the things that they're told.
It goes to another idea, which connects the Euclid mission, but also NASA in general, and just the idea of exploration. One thing Masons are encouraged to be, especially we have different degrees in Masonry, and we have a second degree, is we're encouraged to be lifelong learners. One of the things that we're kind of taught is that whatever profession you have, whatever job you have, whatever you do, it's always good to keep on learning and keep on studying, especially liberal arts and sciences. The argument being that the more knowledge you have about the world and the universe, the better citizen you can be, the better able you'll be to just make more of a positive impact in the world. Whether you're, the CEO of a company or a janitor at the same company, you should always be learning and trying to learn more. How important is it, you think, for people to, maintain, a level of curiosity about the universe and a desire to explore and to learn more? There's obviously a lot of practical benefits to NASA and to the technology it's provided to the world, but just the exploration and learning for the sake of learning about the universe. How important is that, do you think, for society to continue to enrich it and to help us be better, citizens of the universe in this case?
Yeah, that's a great question, and I'm obviously somebody who's very biased in that I'm incredibly lucky in my life to have been able to dedicate my life to saying, what are the really interesting questions to me, and then being given by NASA and our partners, the European Space Agency and universities across the globe, being given the time and the resources to go pursue those questions without having to show, all right, what's the immediate benefit? And so I think it's an incredibly important part of being human to want to explore the universe without necessarily saying what you hope the very practical end goal would be to exploring the universe. And so I'm lucky to be able to do that. And if I look at something like dark energy, and somebody says, "Well, what's the point? What can we build with dark energy? And will it solve our dependence on oil?" Or the answer is we don't know yet. We don't know enough about it. We may be able to harness it for something someday in the future. Almost certainly not in 10 years, or maybe even in 100 years, but someday in the future, maybe we will. And if I look back to something that we've talked about already, Einstein's theory of relativity, Einstein didn't have practical applications to this theory of relativity in mind when he came up with it 100 years ago. He was trying to come up with a mathematical construct that described how the universe worked because he was interested in that. And if you fast forward to today, something that all of us have in our cell phones and everywhere is a GPS device, global positioning system. And that global positioning system, it works by sending signals back and forth between a satellite, and there's delays in those signals and timing that can only be calculated using general relativity as our theory of gravity. So without general relativity, and our understanding of gravity through general relativity, GPS systems wouldn't work at all. And so that's a very practical application of general relativity that no one could have envisioned 100 years ago. And so I think that we want to give scientists and other people some support from society to pursue these pure science ideas, these ideas without necessarily a near-term practical application. One, because they may turn into a practical application some decades in the future. But two, because it's a very innately human part of our existence to want to be curious about the world and understand the world around us. And I sometimes feel sorry for people who have that curiosity as a child and then somehow lose it as an adult. They're like, oh, I don't really care about understanding how the world works. I think, wow, I wake up every day and I have this sense of wonder about how the world works, and I feel lucky that I get to go pursue it as my job, and I wish everyone got to share in that sense of wonder.
I can speak to that a little bit in the sense that I remember being very young myself and being interested in, every kid asks, where do we come from and what's up there? And then, as I got older, you have school responsibilities and work, and I did start to lose that a little bit. And it really was, in my case, my Masonic Lodge and Masonry that brought that wonder back to me. Because in Masonry, they talk a lot about, making an effort to understand the world and being curious and lifelong learning and geometry. And they mention, at one point they use this phrase like material blessing of light. And that got me thinking about what light is and studying that, and, electromagnetism and special relativity and all that type of stuff. So, Masonry, I really credit it with helping me regain that sense of wonder about the world and the universe. And then having, NASA doing the research, I get the benefit of, I don't have to do the work. I just get to read what you guys are doing, and I get to enjoy it as a spectator. So it's much appreciated, all the work that goes into it that you guys do.
Well, yeah, thank you. And on behalf of my colleagues, thank you for supporting us in this way. And you're in Canada. I should also mention that Canada is a member of Euclid and is participating and contributing to Euclid as well in very significant ways. Yeah.
Through the Perimeter Institute, right?
That's where one of the lead researchers for Canada in Euclid is, but there's a number of institutes across Canada that are also contributing. So it's really a countrywide effort.
I should mention, you know, I'm recording this at the beautiful Windsor Masonic Temple in Windsor, Ontario, which is pretty close to Perimeter Institute. I'm guessing it's closed right now, as most things are with current circumstances, or closed to the public. There might still be people working there, but I do believe that they have, you know, public tours and public events there once the situation resolves. So it'd be a cool thing to check out. I should try to go there. I'm assuming JPL also is, once people are able to go back out in groups, have, you know, tours, and people are welcome to attend there.
Yeah, so JPL, and again, this is in the before times, before you know everything was shut down. So JPL is not completely shut down right now. We're mostly shut down at JPL. About 10% of the workforce, I think, is able to work safely there. I'm not in that 10% because all my work is on a computer. So they say if you can work safely at home, you should do so. But JPL has public tours. And if you just Google JPL public tour, you can see how to sign up for one. And I would, anyone that wants to visit JPL, I would urge them to sign up as far in advance as they can. These tours tend to sell out very quickly, you know, months in advance. And I don't mean sell as in money. They get booked out. These are free tours. And it's JPL itself has got a really fascinating history, you know, from these first people experimenting with rockets out in the desert near Los Angeles, to, you know, more recent JPL endeavors of putting the rovers on Mars, and possibility of in the future studying, looking for life on like the moons of the outer planets like Europa. So JPL is doing a lot of these really exciting things, and you can take a tour and see some of the historical stuff and the things that are being built now. And then every year, about this time of year, so it was obviously canceled this year, but in late May or June, there's what used to be called a JPL open house. We don't call it an open house anymore because it's not completely open. Like with the tours, you have to get a ticket ahead of time. Those tickets are free. You just have to sign up. And the reason we moved from an open house, everyone just showing up, to having tickets is about 30,000 people a day would come for these 2 weekend days. And that's how many people would get in. And then I think many, many more thousands or even tens of thousands of people would be turned away and said, oh, we're full. We can't absorb more people today. So now they have tickets. So they don't want people showing up and being disappointed that they can't get in. But if people are visiting Los Angeles area and know far enough ahead of time, they should definitely Google JPL public tours and take one. And I've walked along on a couple of public tours, and I always learn something. It's very fascinating to me, even though I've worked there for 16 years. So JPL is a great place to visit and learn about sort of the history of the space program and a lot of history of what NASA has done.
Speaking of your work there, or your CV, I do have a goddaughter. She's very smart. She's loves science, and she had a couple of questions that she sent me that she wanted me to ask you.
Sure.
She's loved science for a while, and so she wanted to know first what your degree is in, and if she wanted to become involved in space exploration, either on the ground or just whatever aspect of. She wanted to become involved with NASA. What should she look at for her education and for degrees?
Those are great questions. So my degree, my undergraduate degree, is in physics, and my graduate degree, my PhD, is also in physics. So it's fairly easy and common to study physics and then go work in astronomy or astrophysics. Some people are a bit more specialized and they have degrees in astronomy or degrees in astrophysics. But I did a degree in physics, and I specialized in astrophysics, and those are essentially the same. So if your niece is interested in being a
Goddaughter.
scientist, oh, sorry, goddaughter. Sorry about that. If your goddaughter is interested in being a scientist, I would encourage her to think about ways to go first to undergraduate and then eventually to graduate school to get a PhD. So most scientists have a PhD. If she's more interested in the engineering side, the building things and the putting things together and figuring out how to build a mission like Euclid or a camera like the one that goes into Euclid, then engineering is a good path. And there are people at JPL working quite happily and successfully with a bachelor's in engineering, a master's in engineering, and even people with PhDs in engineering. So they're just different levels of schooling that can go with being an engineer, someone that implements the ideas. So that's the big differences, I think, between a scientist who almost always go to the PhD level and engineers who can go for various levels of school. But I think the key is, in any of these cases, is a couple keys. One, study what you love. If you love the engineering side, don't think, oh, I have to go be a scientist, or vice versa. But also getting hands-on research experience, especially in college, I think is key for somebody that wants to work at a place like JPL. That's one of the big things that we would look for in hiring. Did you do an internship? And I should say internships at places like JPL are paid internships. They're not people working for free. But by the time you're in high school and then especially college, be looking for these opportunities to do internships at universities or labs or other places to sort of learn how the research is done and to fill out your resume in a way that makes it impressive to future hiring panels.
Wow, just when you said, high school or college, that's still about, college is about 10 years off for her.
Okay.
Just thinking about, when she's in college, I will be very old, and that does not make me happy to think about that. I already feel old because knowing her when she was a baby to now. So I guess, yeah, high school and college is right around the corner. So,
well, even at age of, assume then she's, close to 8 or 10 or whatever. There's finding age-appropriate popular level books in science and engineering can be a great way to learn about things. And that's what I did growing up. I read a lot of both science and science fiction, even at that young age. And so reading about these things, especially by the authors who know how to write about very technical fields without using all the math that she wouldn't have had in school yet. So I think that would be a huge help. And for me, when I finally got to high school and college and got that math background, it was nice to know sort of already the sort of qualitative things that I was going to be learning about from that reading I'd done as a kid.
Going back to, you talked about kind of current circumstances. You have about 10% of the workforce able to go into JPL and the remainder are working from home. Has that affected, or do you see that affecting the launch date for Euclid? I mean, we talked at the start, mid 2022.
Well, yeah, that's a good question. So JPL did its final hardware delivery. What JPL was delivering for Euclid were the detectors for that near-infrared camera. And it was already last year in 2019 that JPL delivered those detectors and the associated electronics to Europe. And so then it's European lab and universities and so on. And there's their job to integrate that, put it together, test it, and launch it. So for Euclid, JPL being partially shut down and people working from home won't affect what we can do. In Europe, of course, there was a similar shutdown for a couple of months. And the last I heard, we had accumulated a couple months of delay to our possible launch date in 2022, but not more than that. And also, I've more recently heard that things are starting to open up in Europe. People are finding ways to open up labs and so on safely with the proper precautions and the lowest number of people physically on a site possible to avoid spreading any germs. So I think that we won't see long delays between for the launch of Euclid. I'm hoping, sort of knock on wood, that we don't see long delays. There might be a couple months delay, but in the grand scheme of things, how long these missions take, a couple months isn't a huge change.
So I got to ask only because you mentioned it, and I find it fascinating. It's not about Euclid, but it is about space exploration. You mentioned, JPL is working on perhaps sending something to Europa or some of those outer moons of Jupiter. I have heard about Europa before. I understand that there's water on that moon. Do you think that's the best bet in terms of finding life within our solar system, at least, or within our?
Yeah, any time you can find liquid water, that's the best bet for finding life as we know it. And so we have a sort of I don't want to say human, but Earth-centered view of what life looks like, and all life on Earth depends pretty heavily on liquid water at some stage. And so the first thing that we're going to try to do when we look at other parts of our solar system are look for liquid water. Now, Europa has a lot of water on it. It's further out in the solar system, so it's cold. So there's a crust of ice at the outer part of Europa, but through various studies, we're quite sure that underneath this crust of ice, there is liquid water as well on Europa. And so it's trying to study whether there might be life associated with that liquid water under the outer crust of Europa. That's the focus of the next, I think, few decades of Europa exploration. Right now, we have plans to send a spacecraft to Europa. It wouldn't land, but there are a lot of people thinking about how to land a spacecraft on Europa, and there's actually been a considerable amount of effort and money spent at NASA to develop those plans. That's not an approved plan yet, but I think that will be the next stage that people will want to think about after they send a spacecraft out to more closely examine Europa, is to land something there.
So before we wrap up, I do want to thank you so much for taking the time to speak with me. I know you said you're working from home, but that doesn't mean you're not still very busy. I'm sure there's a lot on your plate, and you've taken time out from your day to speak with me is very much appreciated. And also all of the work that you do. Like I said, I get to be a spectator, so I get to enjoy the work that you guys do, and I get to learn about the universe, but it's thanks to the work that you guys do. I just get to sit back with my feet up and enjoy it. So it's much, much appreciated. All the work that yourself and NASA and the European Space Agency and the Perimeter Institute and all these different organizations do for dummies like me who get the chance to sit back and learn about something. But I do, this is a Masonic podcast. So just out of curiosity, in California, around JPL, are there any Masonic lodges of which you're aware?
I think there is one in Pasadena, and I think I've driven by it, but I don't know that much about it. I would have to Google it. Yeah.
Yeah, it's one of those things. So many people there, like the Windsor Masonic Temple here. It's been here since 1921. people
Wow.
pass it every day and don't know what it is until, somebody tells them it's a Masonic lodge, or they've even been here because we rent it out for weddings and special events, but they don't know it's Masonic lodges. Think it's like a dance hall.
Okay.
So cool, Pasadena. I try to track down Masonic lodges and get in touch with them. So
Yeah,
I
yeah.
encourage you to go knock on their doors. It's always fun. They're beautiful buildings usually, so it's a great chance to learn about a cool little piece of Pasadena history.
Yes, I will do that. And thank you again for inviting me on. It's been fun to talk to you, and I hope this is of interest to your listeners.
I'm sure it will be. A lot of I put up a note saying I'd be putting this interview out, and a lot of people responded with a lot of excitement. My father, particularly, can't wait. So he's
Okay.
checking it out too. And with that, I guess my last question is, moving ahead, what are you most excited for, just in the future of either the Euclid mission or just space exploration in general? What are some exciting things that you see on the horizon? We mentioned before we started this interview about kind of the newer approach NASA is taking with partnerships with private enterprise, with SpaceX, the recent launch there. Just what are some of the things that really excite you moving forward with exploration of space and the universe?
It's something that we touched on towards the end of the discussion. We mentioned the possibility of finding life on Europa. Now, we don't know that there's life on Europa, and we're going to look in our solar system wherever there is liquid water, and there's other places in the solar system where there might be liquid water. Of course, we think that there was liquid water on Mars in the past. There's another outer solar system moon, Enceladus, that might have it. So looking for life there. And then looking further forward, there's a lot of plans for space telescopes, especially in the 2030s timeframe, that would have instruments that would allow us to take both images and spectra that look at the lines in a light spectrum from planets that look like Earth around stars that look like the sun. And we could look in these spectra for possible what we call biomarkers, signs of life, things like oxygen chemistry out of balance. What I mean by that is if you look at the amount of oxygen in our Earth's atmosphere, it's there because of life. And so if there wasn't any life, the composition of our atmosphere would look differently. It's not a stable composition without being replenished by life. And so we could look for some of these biosignatures, and we could we have in our technological capability of in the next, say, 20 years of finding signs of life either in our solar system or in other planets, other solar systems. And to me, that's one of the most exciting things on the horizon for science, this ability to look for possible signs of life. And I'm not talking about finding and talking to aliens. I'm talking about seeing evidence for even life at the microbial or level, bacteria level. That would be really exciting as a scientist and as a human, to think about the implications for that, both scientifically and philosophically.
Absolutely. Well, thank you so much for being here. Thank you for the work that you do, and thank you for showing some appreciation for Euclid, an important geometrician and important scientist for Masons. So we appreciate you guys showing him some love in your mission. Thank you so much.
You're welcome. Thank you. All right. Thanks a lot.